Go for it.
Goodbye, O.
It was good to know you the short time that we did. Theoretically, we're streaming.
You're what?
Theoretically, we're also streaming on YouTube now.
Oh, okay. Charles admit. He's unverified. Okay, can you talk now, Charles? It doesn't say disable yet. I even say allow camera. How's that? Exciting. No, it's still disabled. I'm going to disable you, then allow, and see if that does it.
I'm about to make Charles a presenter. Take that, Microsoft Teams.
Charles, what OS are you using?
You know him. He's probably on like.
Oh, Mac.
Well, I thought we were gonna hear like Gen 2.
That's what I was thinking. Charles, I'm using the web versus the native Teams. I've tried to use native Teams in Ubuntu and just give up. But the web works well, especially if you got Edge installed. He's working so hard.
I appreciate that. I'm also just checking to see. All right, YouTube.
Hey.
Okay, I think it's working.
Hey.
Incredible. So the Teams web client in Safari works better than the official native first-party Teams app.
I want to tell you that I'm surprised.
Good job, Microsoft.
Like I want to say like, oh no, there's no way that could be true.
Yeah, Teams is it sure is one of the video conferencing apps of all time.
Yeah. It's amazing the cross-browser standardization of the web, how mature that's gotten at this point. That's all I gotta say.
I've also thrown up just like the stream on YouTube, just if it's, people theoretically will have it if they would like it. I don't know. I want to give a.
You wouldn't be, then you couldn't see my smiling face.
Yeah, no. I mean, look. This sort of stuff, I like it when it works, right? It's great. We're all in one place. We can all chat. Patrick Hayes needs to be able to chat. Patrick, your mic is enabled now. It was for. Yeah, there you are, Patrick.
Hey, Patrick.
So, yeah, I like the idea of being able to do this, though. I will tell you, like, our original goal was to do this on LinkedIn Live. The reason we didn't is you have to have a streaming service and you need 150 followers to your page to activate that in LinkedIn. So we need about 70 more of you to follow us.
Whoever has LinkedIn spam accounts, now is your opportunity.
Where's Derek when you need him?
Am I following Silicon Swamp on LinkedIn? I think I am.
I would hope so. I mean, what is the point of LinkedIn if you're not following us?
I mean, I definitely, yes, I am following Swamp. I'm doing my part.
And it's Tad's dream to get to 69.
Hold on, it says 85 followers.
That's like 2 more than yesterday. All right, we're streaming. I don't see any complaints on the Discord. I want to give people another few minutes before we dive into it. How's it going? How's Colombia? You guys surviving out there?
Yeah, I suppose so. I don't know. It's not the same now that Tad's not here.
That's okay. I'll be back in a couple weeks.
I may be gone in a couple weeks.
Oh, Carl's already like scheduling the trip out. Like, oh, I gotta be somewhere.
Yeah, no, it does actually. No, it depends. Or when you, it depends how many weeks. A couple weeks means, because I do have a trip coming up as well.
Well, I'm planning to be there basically the whole month of April.
Okay.
So long as you're not fleeing the state for the month,
Not yet.
Yeah, not I had Carl's like, oh man, I'd only planned a week out. Now I gotta stretch this business trip. So I'll be back. I'm excited to kind of come back. It's been fun out here in San Francisco. But yeah, I definitely miss home. I actually have met several people from South Carolina that like came out here from like Columbia. They came out here for conferences and things, and they've been like, "Oh, I know that you're out here. We should meet up, have coffee." So in some ways, I almost feel more accessible than when I was living in Newberry.
You don't have to drive as far; they come to you.
You're right, exactly. Like, oh, I should have just moved to San Francisco. Then I could have hung out with tons of Columbia folk. So we've got approximately the number of people that signed up for the webinar. I'm just waiting to see if we're going to get more people. Let me just check if there's like a ton of people streaming on the Swamp.
All right, this is a pretty.
There are
good
4
setup.
people
I can
watching
turn
on
my
the
TV.
Swamp.
Nice.
On the channel. That's cool.
That's pretty great.
And I can hear the audio going out, so that was the other thing I was concerned about. Hey, everyone.
Yeah.
This is also more difficult because usually all this production stuff, the streaming and stuff, Carl, usually you handle that. And it's always kind of the same thing.
This is easier to do, right?
It is, but it's still like it's the division of labor, right? It's like, okay, Carl's doing that. It's not in my head. I'm not checking. I'm just checking like Discord channel. Carl's like getting the stream and making sure it's working. And so it's yeah, one person can definitely. We've done it, right? One person can handle all of it, even live, right? But it is a bit. It doesn't seem like it'd be a lot, but it is, right? It's like one extra person who's doing the stuff on the laptop. And you'd be like, Carl, did you check the YouTube stream? Right? And today I have the privilege of also being the presenter. So that's an extra. So we'll figure it out. We'll dive in. We're gonna start 15 minutes after the hour, everyone, just so you know. And then so we'll start in a few minutes. But yeah.
Are you gonna interview you?
I was gonna skip it, but I was gonna give a spiel about the Swamp. I thought about doing an interview of me by me, but then I was like, just watch the old Swamp. Carl did a much better interview than I'm ever gonna do of myself.
I mean, if you had 2 cameras, you could do like a little Smeagol thing while you're doing it.
Oh, like, well, what did you like about machine learning? Well. Yeah, I think I mean I did see more people kind of sign up for this, so I know people from Charlotte and stuff. So
nice.
I don't know if they'll show up, but if they do, very cool. Then I guess I should even check just right before like the Meetup app.
You need messages.
Yeah, if somebody's like, how do I get in?
I mean, I was a little confused, although if I had just waited another 10 minutes, I guess I would have just seen it on YouTube and that would have been fine. So
we went for the YouTube for sure, and we went for the problem is that like I can't just say like here's the link and there's one link. Some people are gonna be on YouTube, some people are gonna use this webinar app. I do have messages on Meetup. I bet it's just a ton.
Yeah, I didn't even know that you could do a Teams webinar as distinct from a Teams meeting.
This event thing, yeah, this is fancy.
It's nice. I've only done it one other time, but I would say like, okay, it's got the normal Microsofty kind of hiccups, but it is kind of nice. It's like, okay, it sets up a little page for you. People register, they come to the thing, and it's essentially the layout's just like a Teams meeting, which I'm in all day anyway. So it's a pretty familiar setup, at least for me. So I wouldn't say I don't dislike it. I just wish it could be like, here's the meeting link, come if you want, right? Without like the sign up
Right.
and then email you. I understand why people want that, and this is designed. This isn't really. We are just having a Teams meeting here. We have 15 people, but it's designed for you have like 1,000 people in your webinar, right?
I don't know. Now that Ted has my email, I'm gonna get like all kinds of spam about like AI stuff and things.
Yeah.
Man, I wish I was that good at marketing. My outbound is weak. No, man, you're gonna get a bunch of emails about Pocketbookie, our new app we're launching.
Pocket Bookie?
Yeah. What if you had an app so powerful it was like having a bookie in your pocket to help you make sports betting decisions?
I mean, yeah. I
He's
mean,
running.
I guess sports gambling is becoming a thing now. Like that's it's like it's a whole. I mean, it's apparently legal nationwide. I just heard about it on NPR Planet Money a couple months ago.
And at the cutting edge of it is Pocketbookie, powered by Collide. All right. It's 15 after. I think we've given people enough time to, at the very least, complain on one of the various channels, whether Meetup, Discord, LinkedIn, texting me, emailing me, right? I think everybody's had a shot at getting into this thing. If you guys, anybody who feels so inclined, feel free to let me know if stuff pops up in the Discord. I'll try and keep track of it, but we'll hop into it. I think, Carl, I think you guys can see my screen with the great.
And it's showing on YouTube.
Perfect. Oh, Ron's here. Sweet. That's good. Ron from Artificially Digital is joining us as well. Ron, I'm sitting here allowing you a mic. All right. So yeah, we got a good turnout this week. Everybody, for those of you who are new and those of you who are back with us this season, this is Silicon Swamp, right? So for those of you who are less than, we are a tech meetup located in Columbia, South Carolina. We try and do in-person meetups about once a month. That's the plan this year. We're going to see how that goes. But we're also very much shooting for once a week, trying to get out some content to you guys. And as much as possible, focusing on either interesting technology and especially interesting technology that's located with us in the Southeast, right? So most of our in-person meetings are at the Boyd Innovation Center in Columbia, South Carolina, located in the old downtown Five Points. It's a very cool location. If you need information, feel free to hit me up. We have an active LinkedIn channel and Discord and a YouTube channel. In fact, we're streaming live on YouTube right now. Currently, we're putting up the big numbers. We have 4 people. I think one of those is me. So, we're crushing it on the YouTube front. So I highly recommend, we're on Meetup, LinkedIn, follow us, keep in touch. If you're interested in speaking, we're interested in having you, right? We're doing this every week. Basically, the only requirement is that the talk is somewhat technical. That doesn't necessarily mean it has to be AI or even programming. If you're a civil engineer or something and want to talk about that, I think we'd be interested in having that audience. We've had some interest from like physicists, but this is focused on being a tech meetup, especially for those of us from or in Columbia. But a lot of people are welcome. I think, Ron, you're joining us all the way from Raleigh-Durham area, which is cool, man. I'm located in San Francisco today, so and as per somewhat tradition for the kickoff that we do, I will be going first. I'll be the first presenter of the year, so that we can work out all the bugs with me. Next week we'll have Lucy presenting. So that's a little introduction to who the Swamp is. Today, what I'm going to talk to you about is machine learning and how we did AI in the before times. And by that I mean sort of before we got really into deep learning, before we got transformers and ChatGPT, what were those of us who called themselves data scientists sort of doing? So to give you some background, I currently am the CEO of a company called Collide Technology, which focuses on using AI to help optimize industrial platforms, so especially manufacturing. That's mostly what I've done in my career, is optimizing and problem solving in large industry. And before this, my role was the head of data science for a large pharmaceutical company. So most of my professional career, outside of my very short academic career, most of my professional career in the working world has been using data and applying it to sort of problem-solving techniques. Now, I did give a talk at the Silicon Swamp about almost a year, 9 months ago, where we talked about explainable AI. And one of the things that kind of came out of that talk was a lot of people were really interested in, how do I apply these techniques that may be very complicated, and where do they show value? And I thought it'd be cool to give a talk here that's very focused on how we used to do this. And I think that that is not only relevant still today, but it gives a bit of an understanding of how some of these old techniques work, why they're important, and I want to talk a little bit about why they're relevant. So I'm going to start at the beginning, and what will that look like? We'll go into the first slide here. We have a kind of a cute agenda. We're going to talk a little bit about nearest neighbor. I'm going to give some examples of things like decision trees and random forest, support vector machines, and explain and be a little bit more technical than I've been in the past. I'll try and keep this at, split with sort of high-level descriptions of what we're trying to accomplish, why that's important, and also give a little bit of some of the math and technical detail as well. But I'll try not to get too mathy, though I think there are people in the audience that will find that a little interesting. And keep in mind, during this whole time, if you have any questions, feel free to throw them in the chat here, throw them on the Discord. I'll try and check the YouTube too. More than happy to answer questions on the fly. I think Carl's doing a good job of giving everybody a microphone, so feel free to toss a question on the mic as well. I certainly don't mind being interrupted. So what are we going to look at today? Is I want to look at some of the foundational models that we used to use in AI. And explicitly, I don't want to look at first at a lot of neural networks, which is to say that a neural network is a well-established thing. There's a ton of ways to do that. There's a ton of really good ways to do that. What I really want to focus on is, in the real world, how were a lot of us solving problems using these machine learning techniques? And really thinking about what we learned in those early days of machine learning, and then even extrapolated that a little bit into how that's affected the sort of modern environment we have here. Let me see. So kind of just to set the stage, and for those who are less initiated, when we say, AI, I think a lot of people think of this as a very new technology. I think of it as a technology that is recently evolving very quickly, but it's actually been around for a long time. So we could say, when did this begin? In the 1950s, you've got kind of the birth of machine learning, and this is where guys like Alan Turing had some ideas about, well, what if we took these very discrete mathematical steps and we could give them additional pathways? And in these early days, there was a lot of interest in trying to see if you could simulate sort of an intelligence. And there's a reason for that. Alan Turing had sort of come up with this idea of computationally complete, which is to say that he was able to show that a very simple machine could essentially perform every type of calculation. Maybe not efficiently, but it could. And so then people started thinking, well, if the human brain is something like a computer, could these very simple machines, maybe inefficiently, approach the level of performance of a human. And so originally these were like philosophical and math philosophical conversations people were having. What that began doing was a field of study, artificial intelligence, which originally was the goal of, how do we map these processes that humans do into mathematical concepts? And eventually one of the ways people started doing that was biomimicry. And so in the 80s, people started thinking about, well, how does a brain work? It works, it has neurons and synapses and they're connected together. What if I could create sort of a similar network? And sort of the artificial neural network was born. And by the 80s, we had enough computational power that you could effectively calculate a small artificial neural network in a local environment without using special computers. From the 1980s to the 1990s, people were very excited about these artificial neural networks, but they found them highly constrained and I would say somewhat limited on what people were getting out of them. And as we just point out in the chat, Lambda calculus is also Turing complete. But the goal with a lot of these systems is you need to see some sort of real world value. So maybe you're not going to get pure human performance, but I want to see it perform better on some problem. And what had happened was that we weren't really seeing that. In the 1990s, a lot of people were looking at this, and some people, a whole class of people decided, instead of focusing on mimicking human capability, let's try and take this math we've learned in the last 40 years, where we've tried to mimic just sort of the logic that humans do. And let's see what we can do. Now, out of that comes sort of the field of machine learning. And machine learning is a subset of AI where you're taking sort of mathematical concepts that make up the AI fields and saying, let's apply them without constraining them that they need sort of human level performance or the idea that they could grow all the way to artificial general intelligence. And what could we get out of that? And some of them are quite good, and we're going to talk about most of those today. We're going to talk about things like regressions a little bit. We'll talk about nearest neighbor. We'll talk about decision trees. And then, of course, in the late 90s, a big boom happened with support vector machines, which we'll also talk about. And the support vector machine was really, really important in that it was able to make connections across large fields of data highly efficiently and allow people to do some of this machine learning at a scale they hadn't really done before. So, and all of that sort of lasted into, I would say the SVM boom probably went from like 1999 to 05, 06. There was sort of another short AI winter after like 09, and then deep learning came around. And deep learning really was this idea of, well, what if we scale neural networks really big? How far could we go? And that gave rise to people porting them over to general processing unit, graphics processing units, and getting a huge speed up across using these GPU video cards. And from there, they were able to create these massive networks that were highly efficient. And so from about 2012 onwards, a lot of the focus has been on deep learning. These large artificial neural networks with, usually some intelligence in them that helps them kind of evolve. So when we talk about this, and this is kind of a fun picture because I had AI generated, and so then it started making up words when it ran out of things to say. So we're going to talk about nearest neighbors because it's pretty simple, and I think it's a cool algorithm. It still has some applications today. And then from there, we'll move into decision trees, random forest, support vector machines. And then we'll talk a little bit about what people can do with small neural networks. And I hope that this will give you a nice framework to think about options you might have as developers where you don't necessarily have to just use ChatGPT or just use a massive deep learning network. So what's a KNN? Nearest neighbor concept, or K-nearest neighbor, was this idea of, if I didn't know anything about my data, how could I figure out patterns in it? And one of the things that somebody said was, well, what if in trying to figure out a pattern within the data, what if I just tried to see which parts of my data group together? And inherently, this would be a form of classifier, because you'd be saying, oh, well, these groups of data belong to these sections. And we get these interesting opportunities with that, where you get, I'm going to pull up one, where you're able to sort of determine a boundary condition and categorize things in a way that, copy image, all right, and this was supposed to be in here, so here, you're able to sort of categorize things in a way that helps you determine, if I have a new data point, which category does it go into. Now, this solution is great, and it has a couple of big advantages. First, it doesn't require you to know a ton about your underlying data. So you don't need to be a domain expert because you're not really assuming anything. You look at the data and you try and determine which groups are closer to other groups. And in the example I've got here, where you've got category A and category B, it's quite clear. You know, the green and the green dots and the yellow dots are pretty far from each other. But in other situations, you can imagine if these groups were pretty close together, this might become very difficult. Now, the cool thing about this is it just uses Euclidean distance, as there are a couple other distance formulas you can use, but that's the popular one, that allows you to sort of look at these and determine what the average spacing is, and then sort of develop a boundary around them. It's saying, like, okay, if your average distance from these main points is this, then you probably belong to this criteria. So by looking at who are your closest neighbors, and then saying, well, of my closest neighbors, how many of them belong to category A, you can categorize things. And you've done this without assuming anything except for how you could plot the data. And you could do this, you know, we're showing this in 2 dimensions, but you could do this across 100 dimensions. Now, the math behind it is kind of simple. The idea is kind of interesting. Well, where is this useful? Well, think about, you know, on a large scale, if you're trying to classify something like, would a customer buy this product? And you have a ton of information about other products the customer has looked at, both things they've bought and things they haven't bought. So with that data, you can theoretically build a very quick KNN, and you can go and say, all right, well, I have this new product. Let's take everything we know about it, plot it, and then run nearest neighbor and classify it. Is it a product that is likely to be bought, or is it a product that is less likely to be bought? And so that's like a real world application that a lot of people sort of originally were using for. You can do the same thing, and what we would use it for frequently and still do at my company, for things like determining if a machine is going to break, right? We may not know or have enough data to easily classify every type of instance that would cause a machine to break. But if we collect all the data that we are gathering, what we'll find is frequently we can group them. Machines likely to break, machines not likely to break. And then if we start taking data points from the machine, we can just run it through a very lightweight KNN, and we'll see that, oh, okay, no problem. This is likely or unlikely to work. Now, I'll say I didn't want to go too much into this. This is one of the more basic concepts. I'll talk a second about it because it's interesting. But I will say for the other examples I'm going to give you, I have some examples actually in Colab notebooks to kind of show you. But I will tell you that this is an incredibly lightweight model. It requires very little feature engineering, usually. And it has the advantage of not requiring you to have trained data necessarily, which is really interesting. So most learning models that you're going to use, whether it's an artificial neural network or a KNN or an SVM, they're going to work a lot better using what's called supervised learning, which is to say that you know, if you say have a class of customers that have bought a product and a class of customers that haven't, you can imagine you have an Excel table that says, that's labeled, which is to say that, okay, these are the customers that bought stuff and these are the customers that didn't. But frequently, when we go into new businesses or less data mature businesses, that's not available. So people don't have access to the outcomes yet, and they're sort of still trying to bootstrap into that. So how can you show value? Well, this doesn't require labeling of data because you're simply just taking all the math and seeing how it groups together. So you can start initially with these what are called unsupervised learning techniques and start seeing if there's patterns in the data that group together. And then from there, you can sort of show value and extrapolate. So even for my company, this is a common way that we will initially set up predictive maintenance for companies, right? They'll say like, well, we have all this data, we're collecting all this machine data, but what we don't have is label data saying, oh, here's data for when a machine broke and here's data for when it didn't. So how can you help us out? And the answer to that is we'll run unsupervised learning using fundamentally this technique. Now, are there any questions on that before I jump into decision trees? I know everybody's favorite topic. So in these, the next big tool that we use, and I would say that one probably I've used maybe the most in my corporate career, is decision trees. And decision trees are exactly what they sound like. They're essentially a flow chart with rules that says if I've got this data, then I will split the data and I'll send this part here and I'll send this part here. And so you could imagine, let's say, and I'll show you an example of this, let's say that I was trying to, we'll use the same category of like you have a shopper at a store. And I'm trying to determine whether a shopper is a likely buyer. Let's say it's a car lot, right? And you say, okay, the shopper comes in and I know things about them. I maybe know their credit score. I know their gender. I might know if they have a car or not. So I take all these factors. And then what I try to decide is I want to put this person, based on all these decisions, into each bucket. You know, likely buyer, unlikely buyer. So they come in and I, take this data and I analyze it. Now, the problem is like coming up with rules that allow you to split that can be very difficult. And decision trees essentially understanding that a lot of the decisions we make in life, a lot of the human decisions is going to be related to a ton of rules. So the question was, how do we as humans build these decision trees? Because a lot of us are making decisions like this. Sort of, we look at an item and maybe we're trying, even when you think about something simple, is your car isn't running, right? So you go and you try and start the car. Does it turn over? Does it make a sound? If it makes a sound, what sound? And from this, you're trying to figure out what is the car? Is the car broken? How is it broken? And you can see that in our normal human interactions, we follow this sort of flow chart of decisions that one might make to problem solve. Now, while doing that, what we end up developing is essentially internally a flow chart. And so the question was, how could we replicate that sort of decision-making process that people and animals appear to do and do quite well and automate it across just data? And from that is like where the decision tree is born. So a decision tree has this idea of, I take all the data categories I have, and I'll show you an example of this with flowers, where I try and determine, okay, in this case, what we'll actually show, and I'll show you what this data looks like. I have to stop sharing and then reshare because I was only sharing one. I want to actually share a screen. So there's a famous data set. It's what we'll be working with today when I show you kind of the live examples. There's this idea that, there's a data set where, I think this is from like the 1900s, somebody wanted to determine what type of flower something was. And not just any flower, but different types of irises. And they wanted to determine that based on what they'd measured. There's sepal width, sepal length, petal length, and petal width. And to give you an idea what these flowers look like, I think I have pictures of them. I do have pictures of them. These three flowers are they are Setosa, Versicolor, and Virginica, and they're similar. They're all three irises. They all have elongated sepal lengths. They all have similar type of petals, but they are different flowers. Now, a person who's been trained in botany can take a look at these flowers and go, this one's a Setosa, this one's a Versicolor, this one's a Virginica. But a computer doesn't have that much data, and before we had computer image processing, how would you go about this? So there's a nice data set that has been kind of a crux of testing simple mathematical things that we have for this. And so we've taken this data, and somebody actually went and across the classes of Versicolor and Setosa actually created a database. It's free, you can get this online, but it's been around forever, where they measured 4 parameters of the flower and then said which flower it is. And this is not the whole database, but even here there's over 100. And that makes up a really nice data set that you can try out machine learning models. Now, what we've done here, and I'll go back and explain the math here in a second because I don't want to skip over that. And actually, there, I'll talk to Chuck's question in a second. In developing these decision trees, you can see already this data, where we've colored red as Setosa, green as Versicolor, blue as Virginica. There's a ton of overlap. So trying to draw a line between any of these based on any of these other parameters is hard. But you can sort of start thinking like, well, if I just look at petal width, I can draw a pretty good line and get all of my Setosas. If I draw, I can get a pretty good line between, by using sepal width, between Versicolor and Virginica. But there's always a little bit of overlap. So trying to find a way to actually segregate all 3 of these out just on their dimensions, based on just like plotting the graph across all the different features and dimensions, doesn't seem possible. So how does a decision tree do it? So a decision tree uses a splitting criteria known as a Gini index. You can also use entropy, but Gini index is probably the most common, I think, by far. The Gini index is really simple. All it says is that I look at a feature, and let's say maybe it's petal length, and I ask myself with my label data, how much impurity in the class is there? And what you want is to find something that has a really high Gini index, which is to say that it has very little impurity and is very homogeneous, which is to say that all 3 of the classes are equally represented. So if you had class A and B, say, trying to determine the difference between dogs and cats, right? What you'd ideally want is to pick something that easily represents both criteria. So the first splitting criteria you might have, if you had things like dogs and cats, would be, does it have a tail? Yeah, both classes are in this, and you might try and split on tail. And then what you would do is find, okay, based on this criteria that has very little, that has a high degree of homogeneity, is a homogeneous structure and represents all the classes as equally as possible, then you try and pick what is the thing that splits these classes the best. And you kind of brute force it. Now, this Gini index is actually quite easy to calculate because you're just looking at the number of instances of the class there and then trying to figure out how to split it, draw a line. This is computationally incredibly efficient. So even large decision trees can be developed and usually produced in under a second. And even the biggest ones I've ever seen, well under a minute. So looking at something like this data, what I've gone ahead and done, and let's see if I can find it, is found some old lecture notes where we're actually going to take a look. So this is some simple Python code, and we've got essentially the IRIS database has been loaded in. This is such a common experience that Scikit, which is probably the largest machine learning library most commonly used in Python, actually has the IRIS database in it. So you can actually just load it by calling like load iris from scikit-learn. And the actual to develop this is also painfully easy. To do this, all I have to do is declare a classifier. I say I want a tree. I tell it I want a decision tree classifier, and then I just tell it to fit to the data. And in this case, I have the data, which are the measurements, to the targets, and we'll run it because we have to wait for the CPU to warm up, but it should run this in a crazy fast period of time. So it's going to go through all the data points, several hundred measurements of flowers, and then build a model, and then print out a score. And it's able to segregate with 100% accuracy. The other thing that I want to point out to you is that not only were we able to train and make this model and test it, but we were able to do that, in this case, 7 seconds, which included us warming up the process-free computer from Google. But the amount of RAM that this model takes in bytes is 2,646 bytes. So this model applied to, what is, in this case, a very specific problem, is so small you could fit it on our Arduino, right? And this is where I think you start seeing some value in machine learning as it deviates away from what we're now doing in deep learning. You can't really do anything in 2.6 kilobytes in deep learning, but here we're seeing, we're able to make really good decisions. And these models scale pretty linearly, so even if we had way more factors, we're still talking about maybe a 30 kilobyte model that can be used. So these things will fit. They don't require GPU. They are very quick. So if I run this again with the CPU actually running, the entire training took less than a second, right? So it couldn't even measure it. So I can train it, and inference is even quicker. So from this, we can go through and we'll test it with different training splits and things. But what we're able to see is that we're able to get results out of this incredibly. I didn't run the actual training split, sorry. We're able to get really good results incredibly quickly. In this case, things like 95%. And this eventually, and I'll show you what the model looks like for this guy. This is essentially what it's built. And you can see here I've got it outputting, in this case we were training on 150 samples. And you can see it basically builds a decision tree. It's well, not basically, it does build a decision tree, but it's essentially a flowchart. So if I'm trying to determine whether something's Setosa, Versicolor, or Virginica, well, the first thing is we look at this Gini index of petal width, and we see that if it's less than 1.75, it's automatically Setosa, right? So kind of the first line we can look at. And then that does a pretty good job of also separating Versicolor and Virginica, and then you can keep following this. Now, this is valuable in two ways. One, it's not only lightweight, and it's making these decisions for you. So you could imagine if you had a ton of data, maybe on things like good students, bad students, or shoppers that are going to buy, or proposals that are going to sell, or in our case, machines that might break. These things are running incredibly quickly. They run on small computers. They cost very little. But also, from my experience, this also comes to help you from a problem-solving perspective, which is to say that I can look at this flowchart and understand what the model's doing. So if I need to go through and try and understand, like, what are the factors that separate Versicolor from Virginica, I can figure that out. And similarly, if I was trying to separate, say, buyers that are likely to buy or machines that are likely to break, if in the example of machines that are likely to break, I can go through and see how those decisions were made, and it might be like, oh, machines that are likely to break haven't had their oil changed in 3 months, right? And if I see that, then I can say, oh, well, maybe I can now, as a human, be a part of the problem-solving effort and go a little bit further and actually say, yeah, well, if machines that haven't had their oil changed in 3 months, let's just make all the machines change their oil every 2 months. And then we can start involving kind of our intuition and our knowledge and domain knowledge back into the space. And you can see that now with the packages we have, coding one of these might have taken you a few hours before, but with something like scikit-learn, it's 3 or 4 lines of code. So you can do some really powerful stuff utilizing just this very simple model, which has a very simple framework. And to Charles's question, yeah, there's a ton of overlap between the decision tree and state machine. So Charles put in the Discord chat, seems like there'd be a certain amount of overlap between decision trees and state machines. He's absolutely right. And you can see that, you know, when you're trying, he shares a really cool example that if you have like a k-dimensional space, that you can try and segregate that using a KD tree. And essentially, you can essentially derive a state machine if you actually give states and actions from something like a decision tree. And that's where, when we start dealing with things like IoT devices, where you actually are deploying like Arduinos into an environment, you actually will tie together the flowchart that was your decision tree into the implementation that is your state machine, right? And we used to do this all the time when I still worked in robotics. Right, exactly. Charles says the decision tree would basically be your next state function, and that's exactly right. So in this case, there's a lot of value here. These things are lightweight, they're incredibly cheap. You saw we just trained one for free on Google. And the other thing that you get out of this is because of the interpretability of this model, you get a lot more emphasis. So when I was working as an engineer before, this is probably one of my favorite models because it's very interpretable. It's something we could get out. It's something that we could then relate that value back to a non-technical client, right? They may not care about the Guinea index. They may not care about our splitting parameters, but they certainly would like to know how we were making these decisions. So this is easy to communicate across a lot of different levels, and I think there's, in my opinion, still a ton of value in that. Any questions before? There might be somebody in the chat. Yes, there's a chat question, I think. No, that's just Charles trying to log on. Okay, so no other questions. I'll jump into the next thing. You can expand this technique into what's called a random forest. One of the problems we have with the decision tree, and we can actually see us making this mistake in this example. One of the problems you can see is that when I train this model, because I didn't break up my training and test data, I just gave it a bunch of data and said build a model, is that it got 100% accuracy. Now, because of this, I can say that this model is a little overtrained. It's seen so much of this data that when I probably give it new data, it'll start making mistakes. So a huge problem when we have these large supervised models was how do we avoid overtraining? And there's a ton of ways to do it. The classic way is to do what we did here, which is we split some of the data into training data and some of it into testing data. So usually the split is something like 70 or 30, where you take 70% of your data for training, then use 30% for testing. But there's also like 60-40 splits depending on the size of the data, the level of validation you need. And you can see that we started doing that in this code in this class I taught for decision trees, where we get still like 95% accuracy, and then we test it and we're getting 100% accuracy on the test. So we don't want to overtrain the models. And also, in a lot of cases, these splits are hard to make as the data gets bigger and bigger. So the way that you can avoid this is you use what's called a random forest. And a random forest is essentially a technique where you build a ton of decision trees and they all vote. And you use a technique called bagging, also known as bootstrap aggregating, where you automatically grab some random sample of the data, so maybe 10% of it, and you build a decision tree. And you see how good that decision tree is, however it is, and then you go grab another 10% of the data, and you build another decision tree. And so if you're using 10% every time, you might build 10 decision trees. Now, you let them vote on which technique is going to be the best. And the results are, for large pieces of data, especially data that maybe has nonlinearity or a high degree of overlap, random forests are incredibly accurate. And because the decision trees are so easy to train using this voting process, it's still computationally efficient. We're still talking about seconds to minutes for training, as opposed to hours that we usually spend on artificial neural networks. So in this training process, we've built this forest of decision trees that then vote. This is now what we call an ensemble method. And what we see is the error rates go down. And because no individual decision tree was ever trained on the entirety of the data, we're able to actually not have to worry about overtraining, because everything only used a small piece of the data to make its little decisions. You can also then get a prediction aggregate from the value, and once everything's been predicted, they just vote, you add up the scores. The other cool thing is you can still get a highly interpretable result from this. You can get a plot that shows you what was contained in each one of the decision trees, and you can see which were the more likely pathways to get used. So the random forest, is a really cool technique. Now I will tell you this, that as low level machine learning techniques go, random forest is probably the most general and most applicable to almost any problem. I'm not going to say it's the best for every problem, but it's usually pretty close to the best. So there was a period of time where people were doing a lot of data science competitions online, specifically like Kaggle. And when they were true machine learning problems, they kind of did an analysis of, well, how often could you just run a random forest? And what they would find is that frequently, if you just came in and ran a random forest anytime you wanted, you would get, if you just came into a competition cold, ran the random forest, you'd get something like 92% accuracy. And probably the winner of the competition, using a lot of very advanced techniques, would get something like 97. So in many cases, if you're sort of like, I don't know what to do, a random forest is a really generalized technique. And it generalizes well because A, it's this ensemble method, it doesn't have the problems with training and test data, and also the technique itself allows for you to use different types of data. So in a lot of times when we're using data like this, like we'll see in the support vector machine, I need to give it numerical data because it's doing mathematical things that it needs to have numbers for. If I give it sort of a numerical thing, like, oh, is it red, white, blue? You can imagine, like when we were doing the flower data set, if color flower was in there, it would be very hard to build that data in numerically. But a random forest and a decision tree can handle categorical data. So if you have data and there's categories of the data that are like red, white, or blue, then you can actually still run it. So you get this technique that can ingest large types of data. It gets pretty good results every time. And it's incredibly both efficient and intuitive for understanding. And I think I've professionally been doing machine learning for over a decade. And I will say that in many of the problems that we've solved, maybe the final solution wasn't a decision tree or a random forest, but many times that's something that we would look at and get pretty good results. And so we did find that when we were in a hurry, that if we have 30 minutes to look at this data for whatever reason, throwing it through a random forest was always like a really good strategy. And to the point that, Charles is also making, you can prune decision trees. So his question was, could you do some interesting statistics to make the decision tree or forest smaller? And the answer is yes. And there are some different flavors of trees that both do pruning. So afterwards, you can go back and prune the tree. There's a particular flavor of that designed for IoT devices from Microsoft called a bonsai tree, where it prunes it back. And with the random forest, it's even easier because you can essentially go through and run a bunch of tests and see if there's certain pathways that are consistently bad at producing results. And then you can remove them and kind of revote. So there's some really interesting things there to make the decision trees better. Let me see, did I make a random forest predictor? This is all decision trees. Sorry, I didn't make a random forest. I did do one more decision tree with wine. Again, very common data set where somebody was identifying wines based on the components of the wine. And again, these are all, I'll share these notebooks with people after the talk. We'll put them in the Discord channel. You're welcome to kind of try these out. as your if you're interested. So those are the two big techniques that I'd say. These things have been forgotten, and largely we don't talk about them as much. When I interview a lot of young kids now that want to be in machine learning or AI, they haven't talked about these fundamental techniques as much. They're sort of exposed to them in class, but everybody sort of uses like neural networks for everything. But these are highly efficient, and you can imagine lots of real world results. Like I've given you, we've used them in manufacturing. Big marketing companies still use them. Amazon uses them for their recommender engine. These sorts of techniques, because of their high degree of efficiency, their high degree of adaptability, high degree of interpretability, become really, really valuable in how you can deploy things. And why is that important? I would say personally that one of the big changes in AI compared to traditional software development is the cost, which is to say that the cool thing usually about software is that delivering the software in relation to the cost of whatever you're charging for the software product is usually nearly negligible, right? So, if you're charging a client $10 a month for your app, you're probably only spending 50 cents or something to actually deliver that client. But in many cases, we're seeing that that's not really true anymore. As people are having to deploy these large AI networks, which cost a large amount of money to run and train and energy to keep up and cooling, that things that used to be essentially a negligible cost are now starting to cost a lot of money. So I'll talk to clients about software that we want to deploy and having to explain to them that, well, we can deploy this, but it's going to be, to deploy it on the cloud is $1,500 a month, and to deploy it on premise is $15,000. That's a considerably higher cost than most software products. But if you can map your problem into one of these, you get back to the advantages of AI, which is, I can look at these sort of difficult to define spaces and make really cool decisions based on them, with the advantages of software. These are incredibly lightweight. You can deploy them on edge. You can put them on little computers. You can make them serverless, all without a ton of work. And you start seeing that now you're getting the advantages of AI, in its ability to sort of look at new situations and make a decision, with also the advantages of, on a business side, of traditional software. So kind of the last technique before I talk a little bit about neural nets is support vector machines. And support vector machines are a really powerful concept, and I'll talk about why they're powerful. But I will say that in the 90s, people went crazy for these things. They just thought, this is the future. This is how everything's going to be done. We're going to be doing this forever. It did kind of die out, but the idea of an SVM, it's a very powerful technique that is really a simple concept. The idea was, in most of the concepts that we've just visited, you could imagine that a decision tree or even a random forest is just a series of linear regressions, right? Where you're trying to find lines to segregate data from one side to the other. And maybe you could draw several lines, and you can think of a decision tree as essentially doing that. Like I pick a part of the graph, I draw a line, and then I do it again, and I keep doing this until I build a fairly well-defined boundary around my different areas. The problem with that is that as data gets closer together, it's hard to determine a line. So the goal of a support vector machine was, if instead of just trying to draw a line, what I really want is a line that finds the largest width between two different categories. So you can see in this example we have here, we've got blue dots and we've got green dots. And what we want to do is we want to draw this red line that separates these two classes as well as we can, blue from green. That red line, instead of just saying, well, we want the midpoint, what we do is we identify support vectors, which are these in this case, blue dots here. We draw a line. These represent a vector in the blue category that's on the edge of it. We do the same on the green side. In this case, like the most extreme green one is here. And then we try and determine this red line that gives us the largest amount of distance between these two things. So what that looks like mathematically is that you essentially are doing an optimization problem and you're trying to minimize 1.5 width squared, right? So you're trying to take the norm of the vector and try and minimize that. And you can imagine doing that in calculus. And your constraint is that you want this align, looking at high school math, y equals mx plus b. Here your m is w, and you want to optimize, you want to increase the width, so with your normal equation. So you basically set up an equation where you set these two equations equal to each other, and then you try and find the minimum of w, and because it's the reciprocal of it, you're finding the largest width, right? Now, you can imagine this in a traditional mathematical optimization scenario. If you had Lagrange multipliers, this is very much the same formula. For those of you who are really into math, I will make this very short for those of you who are not. But in a normal Lagrangian optimization, what would we do? We would have an equation that we want to optimize. We would add the Lagrangian equation to it, and then we would assume that the gradient of those two equations are equal, and then we would set them to 0 and solve, right? And then we would find this optimal pathway through the Lagrangian using this gradient. That is very similar to the format we've done here, and it basically gives you an idea that it gives you two advantages. Not only is this mathematically similar to a classical style of optimization, but it has the benefit of being very computationally efficient, because we're able to compute gradients very quickly. So this method, it seems like a lot, and I've got a lot of math on this page. For those of you that aren't into the math, you want to draw a line, and you want that line to be as fat as possible. That's what you're going for. That's it, and it doesn't. You don't have to think about it any more complex than that. For those of you that are really into the math a little bit more, this ends up being something that computers can solve very, very quickly. So, and of course, with modern computers, it's also a calculation that parallelizes very well. So you can vectorize this calculation and solve it ridiculously quickly. So the SVMs were very powerful, and they did this really cool thing where they very efficiently could go through large amounts of data and figure out what was wrong with them. Somebody went on to figure out what we now refer to as the kernel trick. So you can imagine data that is linearly separable. So if you look at this, we've got two graphs on the right side of this. If I have the ones on the linearly separable, you can see the green and the red crosses, I can draw a line between them. But if you look at something that's not linearly separable, like I have in this figure 4, there's no one line that will help us separate the crosses from each other. So the question you might ask yourself is, what can we do? Now, there are some cool techniques where people try to take things like the idea of a support vector machine and say, well, what if we extended it to circles? And I tried to find the largest circle I could grow with the largest boundary. And you can see that if you could grow a circle in the middle here, you can get a pretty good boundary doing that. But you could also imagine that that's very much solves this specific problem. It doesn't generalize well. So people came up with this idea of using a kernel. A kernel is a fancy math term for creating a mapping. Basically, we're just trying to take the function we have that maybe plots x and y and add something else to it, and we just map all those points over. So there are a couple different kernels that were tried, but the one that was probably the most famous is this radial basis function. And this is what made support vector machines famous. The radius basal function, if you expand it out, what you'll find here is there's a dot product in there, or you could write it as a dot product. And assuming that the radial basis function, which is a dot product, it does something really cool. When you create a dot product, you're creating a projection of two vectors and creating a projection that's 90 degrees to them. You essentially create an artificial dimension. So you can imagine if we're looking at figure 4, this is impossible to segregate using a line or a sheet of paper, right? There's no flat plane I could draw. But in a higher dimension, if I were to take a problem like that, so in this case, a linear SVM sees the graph on the left. But essentially, in the nonlinear SVM, using the RBF, I create an extra dimension. Well, now, with this extra dimension, I'm able to separate these. Now, that's related to the part of the fact that the radial basis function uses a dot product, which creates this artificial dimension. But it's really sort of a misnomer. I'm kind of caging over the fact that essentially what you're doing is creating a Hilbert space. Because you have a Hilbert space, you have an infinite number of dimensions, but you only have to calculate one part of your convex space. So by doing this, you're creating this thing that's computationally efficient. You only have to calculate part of it, but you're essentially able to explore every different combination of features because it is a Hilbert space and all the vectors converge. And from that, you're able to create this ability to segregate data that normally you wouldn't be able to separate out, right? And so you're able to take really high dimensional data, lots of features, you're able to find these connections, and you're able to do this in a way that happens to be very computationally efficient. So the result of this is you can take very nonlinear data, maybe things like voice, which is what I've used it for pretty heavily, as well as some other cool things, and you're able to very efficiently find a way to draw it. Because you can imagine once I draw a sheet of paper through this, I can then just sort of, it will map down back into my dimensional space as a circle. So it's a really cool thing. This is a trick, and you're able to cram through data incredibly quickly with this. And I want to go, that's a pretty math heavy, the understanding of the support vector machine is somewhat math heavy. Like understanding what a Hilbert space is and how that relates to an infinite dimensional space or infinitely dimensioned space is complicated. But this fundamental tool is not hard to use. In fact, it's just as easy to use as a support vector machine, plus is able to handle like highly nonlinear data. So Charles asks, like, do you know a certain kernel you want to use in advance? The answer is yes and no. There are probably at times optimal kernels for a problem, but essentially everybody just uses radial basis function. When somebody says they're using the kernel trick, yes, academically it means that I'm using a kernel. But in real world practice, it means that I'm using RBF, right? I'm using the radial basis function. So you don't discover the optimal kernel usually. You just use the you use RBF, right? I don't think I've ever used. I don't think I personally have ever used another one. And you're probably right. So Charles has pointed out that he feels like there could be other kernels that are useful beyond RBF, and there definitely are. I mean, like I show you an example of there is a polynomial kernel. People must use it for something. I've never used it. This problem, it extrapolates so well because you have to think that what you're trying to determine from a practical standpoint is I have a ton of dimensions, right? I have a bunch of features, a bunch of dimensions, and I want to take a look at them. But I don't want to have to look at I know that there's sort of an infinite combination of these dimensions, right? Especially when I allow recursion on the dimensions. And so I know that there's some sort of optimal way to look at them. But the problem I have frequently is that I obviously can't brute force and look at all of them. So what you're doing with the RBF, and why the RBF is famous not just here, is that you're able to compute in the infinite dimensional space the mapping, but you don't actually have to actually calculate the entire mapping because it's included. And the reason you're able to do that is, you know that in a Hilbert space there exists a mapping function between like vector x and vector y, but you never have to actually compute vector x, which is what you're assuming exists. And so from a mathematical perspective, the RBF becomes like a really easy way to calculate how to do this. And it does this with a trick, right? The trick that it does is that essentially that there's a Taylor expansion that's infinite for exponential functions, and it's essentially mapping, it's using the exponential function, which we don't have to do infinitely, and it's mapping that to this like Hilbert space. And so, yeah, I think that there's probably are some like really cool areas where there's specific kernel functions that maybe are better, but in a practical standpoint, it's very, very hard to beat RBF, and in most situations, it's going to crush while being very fast. So to give you an example, this was the trick that I used my very first on-the-job data science project, where I was manually going through a bunch of data, trying to find statistical correlation. We had done a study on a bunch of syringes, and we had, I want to say, over 100 parameters we'd measured on each syringe, and we'd measured over 2,000 syringes by hand, months of like intense labor, and then we're trying to relate to a pharmaceutical company like which parameters were causing this failure. And we got some weak statistical correlations, and we understood that it was going to be some sort of stacking. Like this thing happened when 3 other things happened. But identifying that was not going well. We tried a lot of stuff. And we threw a support vector machine on it on my computer using Weka, a package called Weka, which is actually a JavaScript click and drag machine learning tool. And we were able to solve the problem in about 5 seconds. It immediately identified the area of concern, was immediately able to separate the data efficiently, and immediately we were able to then have it tell us what was the most important features that it used. And so it was kind of a cool thing. It's really what got me professionally into machine learning, because then we started doing this and making a reputation of being able to do this, and then likewise my reputation grew around that. And so it was more of an accident. I'm going to talk for a couple minutes just about small neural networks. And then I think we'll wrap up. We're at about an hour, which normally these things run about an hour. We started a little early because we're virtual, and then I'll give you guys some time for questions. But so as you know, small neural networks are computational models inspired by biological neural networks found in the human brain. If you want to get into the biology of it, there's a whole thing called Hebb's postulate, and most neural networks try and follow some sort of degree of what's called Hebbian learning, which is the idea that like neurons that fire together wire together, and that other neurons become less important. You basically have interconnected layers of neurons, and when you look at something like OpenAI, we're talking about billions of neurons. But there was a time where none of us could run a billion neurons on our computer, nor wanted to. So what did that look like in that world? So to build these neural networks, you basically have 2 things. You have your architecture and you have your individual neurons. The neurons have a bias, which means that each node applies a certain amount of, usually like you could imagine it as an addition, and then it has a weight in a synapse that connects it to other nodes. So as a calculation runs through it, a number comes into this one node, and it goes, I for whatever reason, I add my weight is that I add this much to it, and then I send that out with some bias to another neuron, or maybe 3 other neurons, or several other neurons. And this is my architecture as I build is the connection between them, and there's usually an input layer, a bunch of hidden layers, and an output layer. Deep learning, the official title for deep learning is that if it's greater than 3 layers of neurons, or perceptrons as they're called, then it's a deep learning network. But I would argue that that's a little bit generic. So yeah, usually you're taking an input layer, which is organizing your data, then you're running it through some highly connected hidden layers, which shuffle all the numbers around and are constantly transforming them. And then you have an output layer that basically is putting everything into the right format for it to go out. So the idea, the math for this is pretty straightforward. You have some small function, which I've got here, where y is, your function y is a function of a weight on x times a bias, right? So this is your point times the weight for that point plus whatever your bias is. And then you basically just run through these, and you have a whole system of these. So it's always interesting to me, because when people say we're going to ban neural networks or something, I'm like, are you going to ban matrix multiplication? Because that's all this really is. And I think that's going to be an interesting thing that we're going to have to talk about, is that the core math behind these are quite simple. Now these networks get quite large. Now, I don't want to go into like large networks, and there are a ton of different flavors of these. I'm describing something incredibly simple, and I don't want to make that the whole point of the talk. What I want to talk about a little bit is we can even take some of the problems that we've had and apply these to very small neural networks. And to give you an idea, normally the networks that you see and work with are what are called transformer networks, which have an encoding layer and a decoding layer all working together with attention, which tells it where to look in the data. It has all these complicated parts of its architecture, is all I'm saying. So these architectures, I'm defining like a very, very simple architecture for you, but these architectures get huge. And they have different layers that do different things, and they're specially trained. The thing is that as those get more complicated, they become very difficult to understand how they're working. But when I first started, neural networks were kind of rare. Like people didn't do them because support vector machines were highly efficient, highly interpretable, and neural networks weren't. But you can actually do cool things. So as an example, you can do classification problems, and even something as simple as NIST, where you're classifying handwritten numbers, can be done with a very small neural network. You can handle really basic regression. So I've seen neural networks with just a few dozen nodes that are capable of handling housing prices and trying to figure out, highly quick inference, like what house is going to sell. You see this in classic old school places that have tried to use it in manufacturing. They'll have neural networks that can fire off in 100 milliseconds. Pattern detection of very small data sets, and you can keep expanding these, right? So as you get better at your feature extraction, you can build these more complex networks. I built a little quickie demonstration of this. That's a graph. So we're just going to take the iris data set again. And so I've loaded it exactly the same way I did before. And I've encoded the category. Remember we talked about categorical data. We've one-hot encoded the categorical data, which is to say that this is a cool data science trick for you young guys out there. Do not assign numerical values to categorical data. I see this all the time. Somebody has like cats, dogs, and lizards, and they go, oh, I can't handle categorical data. I'll make cats 1, dogs 2, lizards 3. Your neural network does not know you did that. It thinks that now that a dog is worth 2 cats and a lizard is worth 1 cat and 1 dog. You've applied like a magnitude. So what you want to do is create a one-hot encoding where you create a column for each one of those and you apply just a 0 or a 1 value. Now that has the advantage of not having this magnitude problem, has the disadvantage of adding a lot of features. So if you have 100 categories, your data now has 100 extra columns to it. So pluses, minuses. But yeah, we create categorical data. We split the data. We just say we're going to train it. And here we have 2 layers. We have a ReLU activation function, which is very good at finding different nonlinear connections, essentially like a very sharp sigmoid function that's very computationally efficient. We only have 8. We only have 8 things in it. We only have 8 neurons. I should use the right word. And then we want to turn it into the actual classification, our output layer. We're going to use softmax because we want continuous probabilities. We'll create a dense layer for that. So this is 11 neurons, and we'll train it. We'll train it now. Why not? We're not doing anything. So we're going to train these 11 neurons. We're going to have it run through 100 epochs. We're just using a regular CPU. It's taking about 5 to 10 milliseconds per step to train. And like I said, it's going to do 100 of these. So you can already see not as quick as a decision tree, not as efficient, though it's basically reached. I probably could have done this in 20 steps or something. So I've overdone this by making it 100. And see, it's unhappy now. There, it's running. And we're still using essentially like no RAM. Of our RAM, most of it's just for this Jupyter Notebook environment. and it's done running. It's just going to run a test real quick and tell me which one of these work. So you can see that we were able to train. These were so small that we were able to use like this free serverless compute system from Google, and we were able to train it. And I ran this before, and it was just pretty close to 100% accurate. Come on. This is what we get for not paying Google. Okay, try to make a weird output. So normally this trains, we get the same result that we got earlier. It's 100% accurate, but it was able to train it, and now you could run that with inference that would normally take less than a second. So you could get a result. That's what I get for trying to run code live. You could get a result that's highly efficient, really understood a lot of different data aspects, and costs virtually nothing to run. So I've kind of made this cute graph of what these different look like. Neural networks are very complex, but can handle nonlinearity very well. KNN and decision trees are very interpretable. They handle nonlinearity fairly well. SVMs are really efficient, handle nonlinearity very well, are very robust, not overly complex, but you lose some interpretability. So you get these kind of star charts where you can sort of determine what's the best solution for your problem. So yeah, if you're interested, there's a ton of information about classical and modern machine learning. And a lot of this has gotten very, very approachable. You watch YouTube videos, there's a ton of math here that can seem very intimidating. Like we were talking about the radial basis function. That's a very intimidating math, even for me. Like as soon as you start saying the words Hilbert space, we're at some real math. But there's now guys that are just very calmly explain to you what that is and why it matters. And I would say the other cool thing is you don't really have to know that much math. When I got into this field, I knew very little of the math. I've now taught several classes on it, and that's helped me get a better appreciation for the math. And in our kind of interest of creating something technical as a presentation, I wanted to make sure that was here. But what we're really finding is that you can do a lot of cool things with these techniques, just understanding at a high level what they do. If you understand decision trees work by creating flowcharts, and SVMs just make a line with a margin, and neural networks are just running data through neurons, you're pretty good. And you can go do some damage with that. You can create ultra cheap, ultra fast, very competent, very capable models that can do some really cool stuff much faster, and in some cases, in a lot of cases, way more accurately and a ton cheaper. We're talking hundreds of orders of magnitude faster and cheaper than what it would take, something like a ChatGPT transformer to do. And so while we as the world are moving towards increasingly deep learning problems, I hope that those of you that are interested in this field will keep in mind there's a ton of machine learning algorithms out there that can do some really cool stuff. And we've only talked about some of them, the ones that I think are more approachable. But there's also logistic and linear regressions we didn't talk about, genetic algorithms. There's some cool stuff you can do with cellular automata. It's a field that goes very deep. And so I hope that if this is something you're interested in, obviously you guys can always ask me questions, but if it's something you're interested in, I hope you follow up. I've given you some cool resources on pattern recognition, deep learning. Both Christopher Bishop and Ian Goodfellow's books are great. There's tons of YouTube videos on both of them that'll help explain them. Yeah, so that's it. I hope you will all consider using more machine learning in your life. But are there any questions? Hey Ron, thanks for coming, man. Look forward to we hope you'll be able to come and give us a talk as well.
You kind of scared me with the math. We'll see.
Hey man, the math is just there because I think the first talk I gave I tried to do like no math, and I gave a manifesto on how explainable AI is dead. And so this time I thought I'd be a little more technical. But we have plenty of talks that are not. Don't be afraid at all, man. I think you guys have some
No,
cool stuff.
I'm joking. I mean, I'm joking. I actually like the math. You know, coming from a industrial engineering perspective, of linear programming, dynamic programming, like this all makes sense to me. So, and I understand just the interweaving the programming aspects as well, which I think is key.
Absolutely. I think we had a question from Michelle about how we could access these lessons. These are from these are collab notebooks that are online. I will post them on the Discord and make them available. I'll put links in when we finalize the YouTube stream. I'll add links to that as well. If you want, you're welcome to try these out. I can also give you links to tutorials that'll walk you through it, right? Because I have that code. It's not necessarily designed as that was for a machine learning class I gave a while back. And so then there are slides that go with each one of those. I don't mind sharing them, but they're sort of dense and boring. Ron, this is recorded. Feel free to circulate it. It'll also be, this is recorded. We take all the streams, we put them on YouTube. So Michelle, I hope that answers your question as well. You're welcome to access the lessons. We'll post them in the Discord and put the links on the YouTube, or you can always reach out to me or Carl if you have any questions. Any other questions? Charles asked all his questions during the presentation.
Yeah, so one thing I mentioned in the Discord that I'll bring up is what do you think about using some of these techniques for text classification? So I think it would be interesting, Ravik, I got a lot of unit tests, and sometimes they fail because, the code was wrong, there was a compile error, whatever. But some of these, they have to round trip the network, and so there could be a problem with the node they're running on. The network could be having an issue, the server they're trying to connect to could be down. And I wonder if it might be interesting to try to look at the log outputs from running these tests and then classify the nature of the failure based on what type of log messages show up. Like if you see something that says connection error, right, it's probably a transient network problem. But if you see, compilation failed, right, maybe it's a compile issue. But there's with a large complicated code base, there could be a lot of different possible log messages that might imply one scenario or the other, right? So it might not be practical for a human to sit there and hard code every possible failure scenario.
So there are a ton of cool companies that work specifically on that log problem. And there's a couple different ways to do it. There's some really cool. I can tell you how our company does it. We kind of do a combination. We use a really small transformer network, about 500 megabytes, to handle the encoding. So normally when you're using transformers, large neural network stuff, the real problem is how do you take text data and encode it? How do you get the connections? So you use an encoder, and there's a ton of available encoders that essentially defines in the vector space what each token, part of the word, means. And from there, you can actually build, instead of then trying to run that through the actual transformer, you can just take that encoding and use that as your numerical input into something like a KNN. And there's a really cool company called Halso that believes that you can expand this to almost everything. They have some open source software where they've done exactly what you're talking about, where they've taken supervised learning, taken the text, and they've used nearest neighbors, expanded to a ton of dimensions to try and figure out the combination. We use to try and figure out and classify this is an error that's a top priority. This is one that can be changed to this. This is an error that we've seen before, and this is the solution for it. So yeah, Jamie, exactly. I'll show you. I shouldn't be advertising other companies, but Jamie Pearson just asked, "Is it Halso?" And it is. I actually have one of their hats. I like these guys a lot. They're just smart dudes. Really nice, really cool. If you're interested, they're definitely. If you want to see some guys that are trying to take machine learning, in the classical sense, to the next level, I highly recommend going to their website. They have some really cool demos there that are very intuitive. But exactly what you said, Charles, the problem, which is now a solved problem, is just how do you encode the text? And now we have so many good encoding representations that are very cheap for text that you can do exactly that. You can build supervised classifiers using KNN or even what I've seen guys do is use a combination of like nearest neighbors to classify priority and then decision trees to determine like what the result should be.
Yeah, I definitely figured there would have to be some kind of tokenization step in that process, so that you actually have a vector that, you can calculate, distance with or whatever. So yeah, that makes sense. Yeah, figures somebody's already looked into it.
Well, I'll tell you, like at our company Collide, like what we do, because a lot of times we don't have the stuff to do a decision tree yet. What we'll do is do anomaly detection on text, right? So we tokenize it, and then we use nearest neighbors to figure out when there's text that we don't see a lot of, with the assumption being like things we don't see a lot of are maybe more concerning than things we see all the time, and the network keeps running.
Yeah, that could definitely be useful as well. Yeah, I'll have to look into Elso and see if maybe one of their open source tools could work for my use case.
Yeah, it's definitely. I'd say call them up, harass those guys. They're really smart. They know a lot. Like you're welcome to reach out to me if you want to see like how we kind of do one or two of those things too. I'm sure the guys would love to show you. Like, but we have some cool like anomaly detection stuff that basically is exactly as I described it. You tokenize it, and then assuming you don't know anything about it, use KNN to help you determine at least when something anomalous has happened. Any other questions? Bueller. All right. I mean, we don't have to drag it out. I will tell you next week, Lucy should be talking. Lucy's going to talk about SQL. Well, no, I'm sorry. Lucy is going to talk about AI agents and how she's used them in her approaches. It's going to be very good. The stream is now available online. We'll make the recording available. I'll put the slides up, and we'll link some stuff to those example codes that I shared. You guys are welcome to do that. If you have any questions, feel free to email me or contact me on LinkedIn, or always hit us up on the Discord. If you haven't joined, get in the Discord. Follow us on LinkedIn. We appreciate it. And if you're interested in talking, we've sent out sign-up sheets to people that said they were interested in talking, but I think we need speakers pretty desperately at this point. So if you've gotten a sign-up sheet or you're interested in talking and haven't gotten the sign-up sheet, let me know, and I will make sure you get it. We're very excited to have more of you guys contribute your unique aspects and things you work on in tech. And Carl's clapping, so I feel like I did a good job. All right, everybody. This has been a great week. Wait, Charles, did you have a question? You have a question, Charles?
No,
Charles.
All
right. Hey, this is a great way to kick off our first solo Silicon Swamp after last week's joint session with USC. I appreciate everybody being here. Jamie, are you asking a question, Jamie?
No, I'm not. I'm sorry. I just want to say thank you guys. Appreciate it.
I just didn't want to forget you, man. I already accidentally didn't respond to your LinkedIn question a few weeks ago quick enough, so I'm trying to be more mindful now. So, all right, everybody, we hope, keep calm, swamp on. We'll see everybody here, same time, same place, same channel for next week. Oh, shit.